Okay, let's get started on the next session. So I'm Cyrus Dreyer, for those of you who don't know me, from Stony Brook and the Flatiron Institute. I'll be chairing this session on domains and domain walls. And so our first talk is from Eckhard Salje from about ferroelectric avalanches.
Okay. Well, good morning, everybody. I'm very happy to be here, like everybody else, and many thanks to the organizer to give me the opportunity to be vertical speaking and with you. So that's good stuff. Now, I want to talk about phenomena which are fairly far away from equilibrium. They're all very classic, but perhaps the description is somewhat new. So here you can see, if you take an LEO crystal, just a thin transparent piece of LEO, the most standard material you can have, and you put a small needle on it, and so you have a creep experiment, you put it under a microscope, and you film what is happening for 24 hours. That's all what you do. And then you see the evolution of these domain structures, and the films don't repeat themselves here. Let me repeat it. So now what I want you to look at is that these needle domains are not moving in a ballistic way. If you look from far enough and you don't care about the details, it looks fairly ballistic. They go through like that. But in reality, you see some of them which are faster and some are slower. Do we have the... For instance, these secondary and tertiary needles here, they come out in a shot, very quick. Then you have some of them which go for a while, or this one, it would go first fast, then slow, then fast again. And then there are some like these ones which go again very fast. Now, if you just show it again so you can look at this effect again. So you can see some of them go very quick and some very slow. Now, this is 24 hours. Now, if you look on a much higher time resolution, even those which go slowly, you would think they go with a normal friction, Landau-Ginzburg, overdamped behavior, but they don't. What they really do is they have stop and go. They go a little bit, they stop almost completely, then they go again, and they go over different distances and so forth. And so that is the phenomenon we see in all ferroelastics. It's an absolutely universal thing, and I will show you today that the same you can see in ferroelectrics, in particular barium titanate, and many other materials. And what is surprising is that many of these movements you see, this avalanche movements they are called, or crackling noise, different countries have different favorite terms, but let's stick to avalanches, that there's a whole bunch of rules how this works. And it turns out, because it hasn't been done in the past, when you compare with what you observe and these guidelines or rules on avalanches, then so far it looks like they all work extremely well. Now, why do you care about that? I mean, one could say these are quite difficult experiments. First of all, they have to take a long time. People have seen that before. They went through a phase transition. And then in terms of strain or whatever, they get big bumps in a dynamic sense. But in fact, because you measure so slowly, the big bumps are in fact lots and lots of small bumps, and these are the avalanches. Now, what is mind-boggling about that, at least in my mind, is that all the emerging properties in these domain walls, of course, are transported with the domain wall. They're stuck to the domain wall. And that's one aspect we normally don't consider. We have emerging properties, we have a domain wall, wonderful, the domain wall can be like this one here, superconducting. I mean, these are just from my lab, but there are many other properties in there. But they're also dynamic, they're moving forwards and backwards. They're polar, like here in CTO. And then there are domain walls inside domain walls, which again do exactly the same. They're also extremely fast and then slow and then fast again. So all the ferroelastic domain walls have kinks inside. So it's just a normal kink in a wall, so it's a wall in a wall. And if you leave these ones alone, they start moving. They're not very happy at a constant position if you have an external force. So you start, they nucleate somewhere, here's a kink, they move, and they move typically in an order of magnitude which is faster than the speed of sound. So if you go to the terahertz and you want to learn about terahertz spectroscopy in these materials, then suddenly the walls in the walls are actually faster than the wall itself, but the wall itself is also jolly fast. So there is a hell of a mess of different dynamical features going on simultaneously, and it's great fun to look into that. There are consequences to that. For instance, here that's work with Nick, where we have here dipole moments on surface when the domain wall sticks to the surface. This one is moving forwards and backwards, but because the surface is polar, that's not ferroelectric, it's ferroelastic. But nevertheless, the domain is polar, the domain wall is polar, and the surface is polar, and these two together make a chirality when the domain wall hits the surface. And if these ones are moving, then you have these polar vortices going along the surface. It's like a railway, you know, it's going through there. And you have sort of seeming ferroelectric hysteresis in material which is absolutely not ferroelectric. And it comes from the fact that you have these domain walls in there which are moving forwards and backwards in a fairly high speed, and all of them have a polarity inside. And so if you measure macroscopically, not discussing how you do that from first principle, but just you take these samples, you measure macroscopically what the polarity is, then of course you have polarity in there, and you can see there's a narrow loop in there, and this loop comes from the movement of the dipoles which are attached to the wall, and the wall is moving. So that is sort of the scenario of kind of things I want to talk about. So now, some of these walls, I mean, I wrote an article with Karen Darman from Illinois, and I think the main message for a practitioner of this kind of thing is be extremely patient, because these jerky things you can see, they succeed each other like in a machine gun, to bang, 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 bang. If you don't do it slowly enough, they all coincide. They all come into one big heap, and then you can't see anything. So what you have to do is, if you put forces on things, you have to do it in a very, very controlled way, very slowly and very small forces. And this one is my favorite piece of kit. From here to here it's about 5 centimeters, so it's a very macroscopic quartz crystal here with a field on. It expands longitudinally. Then there's a second quartz which is simply there to measure what the amplitude is, and then you put the sample at the end. So you create a standing wave in there, a low frequency wave. The length of the crystal determines what the wavelength is, and you can not only measure what the wave does in terms of action of domain boundaries, but you can do it as function of the amplitude of your force you put in there. So you can have very small force, a very large force. And the small forces here in terms of strain are in the order of 10 to minus 8, 10 minus 9. So extremely small. You can't measure them in X-rays or anything of that sort. But you can go up to 10 minus 4, which is quite a substantial strain. So if you do that in strontium titanate, then of course you have the quintessential material here, where strontium titanate has the fastest moving walls. I mean, they clearly hold the record. If you take a strontium titanate, I mean, in the past 10, 15 years ago, we first looked at that, and I told everybody, you look at strontium titanate at low temperature and the domain walls move. Now, that's not quite true, because they're in a cryostat. Looking is not enough, but you shout at them. Now here you can see that. The lower curve here is the effective elastic modulus. Strontium titanate has 210 gigapascal, which is sort of the interatomic chemical bonding, which determines that when it goes through the phase transition, it collapses to 85 gigapascal, which means everything is moving, the stuff behaves in a very battery soft way, which is not related to any interatomic bonding. It just comes from the fact that the domain boundaries are so mobile, you put external stress on, they give immediately in and relax into a new state, so you measure something very, very low. And here we have a resonance we choose it in a way that the thing is on top of it resonating here. You go a little bit down and what you see if you don't do anything, then the stuff slightly hardens, which means now the friction goes a little bit, it comes down here. There's a little bit of friction there. Now, what you can do with strontium titanate is the only material I know of. You have it in a cryostat in the lab, and you can see there's a little bit of friction. You literally shouted it from outside towards the cryostat, or you kick with a screwdriver a little bit on the wires which come out of the cryostat, and you can see what happens is the green curve here, the modulus goes slightly down from here to here, and the friction goes slightly up, which means the domain walls which were locally pinned are depinned simply by the noise in the room. That's strontium titanate for you. I mean, it's unique. Other materials don't have it in such an extreme way, but they have. And then you go to low temperatures, and here around 40, actually it starts 46, about the damping goes up, and there's a further collapse in the bulk modulus. And this comes because now the domain boundaries are not moving individually, they're moving collectively. They all hold hands, so you have lots of needles, and it's not that one needle goes forwards and backwards, all of them go forwards and backwards, and that's exactly this idea of having a complex landscape where they all slide over them. And so in this area, this one we call the quantum domain glass, and here's a domain solid, because now the domains are all sort of collectively going together. So here I want to show just, here's 3 examples from 3 regimes. When you go to 94 Kelvin up here, as a function of strain amplitude, and here the damping, you see it's basically independent of the strain amplitude. That's a classic ferroelastic material. You have a domain boundary, you kick it, then the domain boundary moves forwards and backwards, and it doesn't matter how fast you kick them, how strong you kick them, they go with a constant speed. So that's what they do, and that is this one. When you go into the quantum regime, it's not at all true. I mean, note this is a log-log scale. When you then kick them, they go in a viscous way. They behave in a viscous fashion going forwards and backwards. And when you look at the power law exponent here, that goes to 0 at 0 Kelvin. But the one I want to talk about today, and I want to put the emphasis on, is this intermediate regime between the classic regime and the quantum regime, which is this one. So you change it a little bit, and then suddenly everything breaks loose. They condense again, and then you put something else, and they break loose again. And that's what we call the jerky regime. Jerky regime, actually the word jerk was together with Ben, and we were walking around. I wasn't quite sure whether it was New York or Washington, but anyway, and I said, I need a name for this random behavior of things, and he just said it's all jerks. And so that's where the jerky regime comes from. Now, in a much more civilized way, these are called the avalanche regime or whatever, but in the lab they are called jerks. So here you can see on a slightly finer temperature scale, so you have the classic behavior here at high temperatures, so everything is more or less horizontal as function of strain amplitude. Low temperature, you have this viscous behavior where they all slide in a viscous way over a complicated landscape, and they behave really in a very nice way. But where they don't behave in a nice way is exactly between these two, where they sort of still slightly pinned, then they depin very, very easily, then repin again, they form different configuration, they nucleate new ones, you have a very complicated landscape there, and so that is the avalanche regime. Here you can see how that works. Here we are just between at the lower end of this temperature, you can see the domain boundaries. The domain boundaries come in, you know, just optically looking at them. The domain boundary comes in, or also from the bottom here, in simple cases or in complex cases. And again, what you can see, the local movement of a domain boundary is not continuous. It goes to bang, bang, and then a little bit continued, then bang, bang again, and so forth. And you can see that in particular in this area, here, there. You can see it here, you can see it here, you can see it here, and so forth, right? So you have this, this typical behavior, and it's different for the simple case and the complex case, and the exponents I will show in a moment are also not exactly the same, but they're very similar. So that is what you constantly observe in these materials. Now you can evaluate that in a very simple way. It's called spectral spectroscopy. People on synchrotron and neutron scattering are doing that all the time. So what you do is you have your picture, you register your picture somehow, then you take the individual pixels and you do the same experiment again. I mean, you take it out, you put it in again, and you measure what is the difference in the pixels. Of course, there's noise in the system, but if you have the same experimental conditions twice and you take one pixel pattern here and you subtract the other one, you only see the noise. And you do that a number of times, so you don't see any microstructure here. And for technical reasons, you also do that in little windows. Then you take the same with the field on. So in strontium titanate, because it's dielectrically anisotropic, you can put an electric field in and move all the domain boundaries. It's very, very easy to do. And then you can see the emerging of all these domain boundaries in there. You can then take the time sequence, you can take the spatial correlation, all these parameters you want to measure, you can measure actually quite easily. And there are, I think a few days ago, we had 2 or 3 papers on that, so it's quite nicely demonstrated. If you do that, then you can say, all right, how much is moving? Is there really a lot moving in the high temperature, or in a high temperature regime? We said everything is classic, so nothing should move, and that's the case here. Above 60, you don't see anything, and from 60 onwards, it increases somewhat, and then below 40, I mean, there, where Müller talked about his 40 Kelvin thing, but you know, it goes up here. And you go to low temperatures there with the field, you really create entirely new domain boundary patterns which are in there and which are highly dynamic. Okay, so I showed this one as last picture, and then we can go in a bit more serious way on the interpretation. This one is work also with Nick Barrett. You have seen that if you saw it on his poster yesterday. That is the transition as you can see it, for instance, in the phase transition of barium titanate. It's only the surface structure here in Peel. So what you can see is there are domain structures in there, and these domain structures move forward and backwards. Now, when I was a student, we always learned that there's a phase front there, and the phase front moves in a continuous way. Now, if you actually measure then you see they're not moving in a continuous way, but you have the entire pattern formation thing we learned from Hohenberg and other people there, which happens here. You have period doubling, you have the forking of domain boundaries, you have all sorts of things which is happening there, and it's happening in a jerky way. I mean, there's something happening here, then there's something happening there, and so forth. Okay, so last picture, if you have an interface between LEO and SDO, then you know you have the free electrons or quasi-free electrons, and you can measure the free electrons, or via the free electrons, you can measure the domain structure in strontium titanate, because they influence the electron path in the interface so much that, so that in that case you can see the interfaces here and the Okay, so let's take this one. So the question then is, so how can we measure the okay, so here, sorry that this didn't work. So we have the interfaces. The interfaces reflect the domain boundaries in the interface between STO and LAO. And when we look at them only at the dynamics, then we can make an experiment where we use a barium titanate single crystal. We have electrons on both sides here, and we put an electric field on. When we have the electric field on, we have electrodes on either side, and if domain boundaries move, they take the strain with them. This strain then leads to jerks, and these jerks can be measured. These can be measured by the piezoelectric sensor. So what it really is you put a microphone on the material. The sensor is basically a glorified microphone. When you have this microphone on there, so that's the microphone here, you put an electric field, you measure a hysteresis, and while that one is happening, the microphone amplifies the strain data which come in there, and so you get jerks which are related. Each jerk is related to a change of strain inside the material due to the electric field. So I hope that is hopefully clear. So here we have the measured hysteresis, polarization against time. So you put an electric field in with a constant speed, and you measure the polarization. While the polarization is measured, you measure also the jerks which are seen or heard by the microphone. And what we do is we measure extremely slowly. So each time this one from here to here is one hysteresis, second hysteresis. So we measure 6 hysteresis overnight. And then we have to analyze the jerks here. Here you can see the jerk density. So the first loop, the second loop, and so forth. And we can measure the probability function for the jerks. So we have the jerk energy. And here's a method, maximum likelihood method, to measure the exponents. So what we see is that while we measure the hysteresis, we see that there's a logarithmic dependence of the jerk energy. The probability is purely power law distributed, as you would expect that. And so you have also the amplitudes. They're also power law distributed. And here's the waiting time. So you have inside these suddenly changes of the strain. And you can see here the probability for time delay between the initial jerk and the secondary jerk is basically what we steal from the geophysicists as the aftershocks. So this one is the aftershock regime. This one is a continuous regime. And this regime here is the random regime. So what happens is you put your field on. Some domains are moving, in particular the big ones. They create smaller domains which are moving after them within the time domain from 10 minus 6 to 10 minus 3, 10 minus 2, and then in the continuums 10 minus 1 and 10 to the 2. So we have first of all the enormous amount of aftershocks after the big shocks. Then after some time they are no longer correlated, they are randomized. And then after a long time we find that they are totally independent of their waiting time between different sequences. So we can do that for various correlations now. We can do that for time amplitude correlations. We can do that for durations, how long these jerks are taking. And we can do that for the probability of aftershocks. And you can see the log-log is pretty good to a certain point. And the aftershocks are all the big shocks, then the small shock, which comes with the probability of 1/T. So here we have so if we put all these shocks together, the exponents which describe the avalanches, we have a bunch of exponents here. The exponent for the energy, so you put the external force, the energy force in there. And the energy exponent has two predicted values, 1.33, which is the normal mean field value, and we have the force integrated mean field value, which is the one from earthquakes, for instance, 1.67. I mean, it's 1 plus 2/3. And the experimental value for barium titanate here is 1.65. So we are really exactly in the earthquake case. We can measure not the energy of these jerks, but we can also just measure the maximum amplitude. If we do that, the maximum amplitude should have an exponent 2.33, and we measure something slightly smaller, which is within the experimental error. And then the correlations of them all come out correctly. So that means that the behavior inside a barium titanate, if you put it in our mind, is predominated by very, very small movements of very small areas near interfaces, right? I mean, it's a power law. The small movements are power law with power law probability more likely than the big movements. What we have done in Ishibashi and theories in the past was we looked at the big movement. And the big movement can be described in a quasi-ballistic way. But what's really happening is not that. What's really happening in its majority of the atoms, they experience the small movements. We are next to the walls. And they follow exactly the crackling noise behavior, the avalanche behavior, and so forth. Here in the end is one self-consistency test. All these exponents are interrelated. You remember phase transitions, we had the Rushbrook and other correlations between alpha, beta, gamma, and so forth. The same thing exists here. All these exponents are interrelated. You can test them, and this one is the test, and 1.33 is the theoretical value, and that's what we find. So I leave you with one more picture. Oh no, let me just summarize here. So, well, here's one picture where they are moving. You can see it takes a little bit of time, that these ones are sideways movement. These are the jerks in here. There's another jerk in there, and that's another barium titanate. So thank you very much.
Do we have some questions? And while there are questions, if the next speaker could come set up.
In case of STO, you have shown 3 regions. One is at 40K and 80K.
Yeah.
And what these temperature correspond to bulk properties?
Well, the high temperature one is the 105.6 Kelvin transition from cubic tetragonal. And then we had a resonance in there.
Resonance.
Yeah. And then in the next regime, we have the classic regime, just domain boundaries moving in the usual way. So no jerks. Then we go lower to about 56, 40, and so forth.
My
then
question
the
is
jerks
how those regions related with the bulk property? That is a TC or some kind of
well, only the other one is, the higher one is a TC. I mean, that's a symmetry breaking.
Yeah,
the lower one
how
is
about
not symmetry breaking, entirely dynamic. Dynamic properties change.
40K is what it
Well,
determines?
the movements become coherent and much faster. So when you put external force on, then the domain boundaries are moving much more easily than at the high temperature one.
Okay.
But it's not a symmetry breaking phase transition.
Just out of curiosity, you were listening to these things with a microphone. Is there any terahertz radiation that would come flashing
Well,
out?
it would be, exactly. I mean, that's one of the things why one goes into this avalanche theory, because it's scale invariant. And so if you go higher and higher up there, there's no reason to believe that it breaks off earlier. So you can go to higher frequencies as much as you can, and they're still on the same line. Of course, we can't measure terahertz for the acoustic noise, but absolutely.
Okay, one last question, and I think we should move.
So I'm wondering if we care about the overall switching time or overall switching speed. Are these jerky events play a dominant role, or they're
Yeah.
more like a?
Well, if you're in this intermediate regime for strontium titanate, it's 100%. It's all jerky. If you go into field-driven barium titanate, it's also all jerky. So it's not the question of whether the jerky is dominant or not in most materials. In most material, it is jerky. But you have some regimes, like in the coherent regime, the quantum regime, in STO, where they're not jerky, but where they're coherent. The entire thing is moving in a more or less coherent way. But otherwise, I mean, virtually all ferroelectrics are coherent. Also, relaxer materials we have now measured, they're jerky, so it's the dominant mechanism. But again, let me say, if you look from a large distance and you integrate over long times and so forth, then they don't look jerky, because then you integrate to some sort of ballistic type of movement. You just simply don't see these finer details. But if you go into the finer details, then it's always jerky.
Okay, I think any other discussion will have to leave for lunch, but let's thank Eckhart again.